An essential tool and what we're going to be working with this year and throughout, again, your engineering career is the idea of vectors. These are crucial when we have to work with anything that has an associated direction to it. If you think of regular functions with graphs, then we simply have a curve associated with an input and an output, but that doesn't tell us anything about possibly going backwards or forwards or up at a certain angle. Vectors are an incredibly powerful tool for encapsulating that idea across all disciplines, quite frankly, in engineering. If you've had a chance to look at the QEng prep from the summer, you will have seen some modules on this, though it may be a little less familiar depending on your high school curriculum. Fortunately, vectors are a fairly intuitive concept, and most people pick them up fairly quickly. The idea is simply to contrast two quantities here, vectors versus scalars. A vector is a quantity that has both a magnitude and a direction. And if you imagine a force or a velocity, so you're moving in a certain direction at a certain speed, or you're applying a force in a certain direction, those are vector quantities. Scalars are the contrasting types, and they're simply things that have magnitude only. Length, volume, speed, those simply have units but don't have directions associated with them. Temperature would be another example of a scalar quantity. It's 5 degrees. There's no direction associated with that. In terms of representations, it's often convenient to use arrows to represent vector quantities, precisely because they capture that directionality, and then the length corresponds to the magnitude. It's a very helpful reference tool to be able to draw these quantities with direction and magnitude. One of the interesting things about this vector representation is that it doesn't matter where the vector is located. We can imagine this force, as a force vector, being applied or drawn here, but it would be the same or considered the same force vector if it was moved over to here. There's no difference in the way we think about these vectors if we change where they are rooted. Let's try to make that a little more concrete. For instance, we can draw a vector that starts at 0, 0, the origin, and goes to the point 3, 4 up here. That is a perfectly reasonable vector. And notice it has an arrow, so this would be the start and that would be the end point. We can also draw these other vectors, let's say from 2, 2 to 5, negative 2 is down here. That is another vector. Those are very clearly different vectors. How about negative 1, 3, negative 1, 3 to 2 and 7? Well, that vector is interesting because this is over 3 and up 4. This is over 3 and up 4. So in fact, these we would call the same vector. All right, they're parallel, they go in the same direction, and they have the same length. Last but not least, if we draw the fourth vector from 1, 2 to negative 2, negative 2, that's an interesting one because the arrow direction on this is the opposite arrow direction from these other two vectors here, 1 and 3. Let's label these quickly. 2, 3, and this last one here was 4. 4 is not equal to 1 and 3. It has the same magnitude and it's parallel to the same vectors as 1 and 3, but it points in the opposite direction. We'll find another way to represent that kind of relationship, but for now it's enough to note that it's not equal. To continue working with vectors, we often have vectors given to us, and then we want to combine them in various ways. One of the ways is going to be through simple addition and subtraction. And again, thinking of forces is a helpful way in most cases to rationalize what we do with these. Imagine we're pushing in this direction and we're also pushing in this direction, and with corresponding magnitudes. The net force or the total force we would represent as the quantity vector 1 plus vector 2. Well, to do that or to draw that out, we simply draw vector 1 and then we take this vector 2 and put it head to tail here with the end of v1, and when we do that and draw our v2, we get a sequence of vectors put head to tail, and the total is the quantity we get from the very, very start through all the chains. Here there's only 2 elements, but there could be more. Through all the chains to get v1 plus v2. And again, imagining this is a force vector, if we're pulling this way and pulling this way, it makes sense to think of the net force, the total force, being a little bit up, but mostly to the right, and that's capturing the combined effect of v1 and v2. Similar effect when we look at subtraction. So if we talk about v1, rooted at some point, and v2 would go in this direction. Well, if we're subtracting v2, this is where we capture the opposite direction idea. We would take the exact same length, exact same line that we're following, but in the opposite direction. And so we'd often write this as negative v2, or we can think of it as subtracting away or removing, going in the opposite direction of v2. When we combine those head to tail, v1 minus v2 here is the green vector. That's the result. Note that the order matters. If we're looking at v2 first as our building block, and then we subtract v1, well, v1 would ordinarily be this vector to the right, but we're subtracting it, so we head in the opposite direction, but with the same length. That would be v1, and the resulting vector is from our start, v2 minus v1, so follow v2, follow minus v1, and that will give us, if we make that a bit straighter, the quantity v2 minus v1. And that's how we can do the geometric combination of addition and subtracting of vectors. Now we can get an interesting effect if we take one vector minus itself. Graphically, we have the v1 vector, and then if we subtract it, I'll draw it this time in a different color, minus v1, what we end up at is this single point. We end up back where we started. So in some sense, v1 minus v1 is just the dot here. Let's actually keep it up here in the original diagram to avoid the confusion. And notice the same thing is going to occur if we take v2 minus v2. If that's our v2, and then we say, I'm going to subtract that v2 away again, then where do we end up? We end up back where we started. And so that point there is also v2 minus v2. And this is a special case for vectors. If we look at those two differences, these are called the zero vector because there is zero length. If we think of a dot, how long is a dot? Well, it's an idealized point. It has zero length. An interesting consequence of this, though, is that this is the only vector which has no direction possible. I can't talk about north, east, south, or west when we're talking about a single point. Every other vector that you draw, if it has a length, it has a direction as well. Doesn't matter how small. However, the exception would be this zero vector, sometimes written actually as a zero with a vector hat on top. That is a single point, and it does not have a direction associated with it. So the one exception to the magnitude and direction rule for vectors. And so that's our quick intro into the idea of a vector being drawn as an arrow, some quantity with a direction and magnitude, with this one exception, and how we can combine them with sums and differences.